Let's look into the expectation and variance of discrete random variables. Here's an example of a probability distribution for a discrete random variable x that we're going to work with a little bit later on in this video. Capital X represents the random variable. Lowercase x is representing the values the random variable can take on. So here our random variable x can take on the values 0, 1, or 2, and it takes those values on with these probabilities. One of the points of interest for us might be in finding the mean and the variance of the random variable x. The expected value of a random variable is the theoretical mean of the random variable. It is not based on sample data, it is based on the distribution of the random variable. So the expected value is a parameter and not a statistic. To calculate the expected value for a discrete random variable x, we have this formula. Our expectation of our discrete random variable x is equal to the sum of x times p of x over all x. And so what we're doing is we're taking all the possible values of x and we're weighting them by their probabilities of occurring and summing it up over all those x's. And so what we end up with there is our overall expectation, or in other words, the mean of the random variable x. And we call that parameter expectation of x, or sometimes we might refer to it as mu, the Greek letter mu, meaning the mean of the random variable x, or the mean of its probability distribution. This can be extended to the expectation of some function of the random variable. So here g of x represents a function of the random variable. It could be x squared or the square root of x or log x or something along those lines. And the expectation of a function of the random variable, well, we just do a similar thing to what we did on the last page. We take the values of the function and we multiply them by the probability of those values occurring. And we add that up over all x. One important quantity for us is the variance of x, which is the expectation of x minus mu squared. What is this doing? Well, this is the average squared distance from the mean, and we're going to call that the variance of x. And to find that, we simply evaluate that function at every possible value of x and multiply those by their probabilities of occurring, and then add it up over all x. Now, this variance of x, again, this is going to be a parameter and not a statistic. This is based on the real probability distribution. And we sometimes represent the variance of a probability distribution by the symbol sigma squared. Here's a handy relationship for us, both in doing some of the calculations and in some theoretical work. This expectation of x minus mu squared that we looked at on the last page, we can use that formula from the last page, but if we square this out and carry the expectation through, this can be shown to be equal to the expectation of x squared minus the expectation of x all squared. Or another way of writing this is that this is equal to the expectation of x squared minus mu squared. Note that this quantity here and this quantity here are not the same thing. Now this can be handy in some of the calculations because perhaps mu might be some ugly number with lots of decimal places or what have you, and using the formula from the last page might result in a lot of round-off error. And also, we've often already calculated mu, so to calculate the variance, which is this thing, we might just need to calculate the expectation of x squared in addition, and this can be a fairly easy calculation to carry out. Let's do an example of some of these calculations. Suppose that 60% of American adults approve of the way the president is handling his job, and we randomly sample 2 American adults, and we let the random variable x represent the number of those adults that approve. And so our random variable x is going to take on the values 0, 1, or 2. Those are the possible values for a random variable x, and we can calculate the probabilities of those, 0, 1, and 2, from the idea that we have 60% of American adults approving, and we are randomly and independently sampling 2 American adults. And I show how to go through those calculations in my Introduction to Discrete Random Variables video. If we were to do that, we end up with this discrete probability distribution here. Now we might want the mean and the variance or the standard deviation of this probability distribution, so let's walk through some of those calculations. Now suppose we want to find the expectation of our random variable x, or in other words, the mean of the random variable x. We're going to use this formula where we take each x times its probability of occurring and add it up over all x. Or in other words, here we would take 0 times its probability of occurring, plus 1 times its probability of occurring, plus 2 times its probability of occurring, and add that up over all of our values. If we were to do so, we get that this is equal to 1.2. The expected value of x is equal to 1.2. Now note that this 1.2 is not one of the possible values of x. When we say the expectation of x, we're not saying a value of x that we would expect to get. We are talking about its expectation, the theoretical mean of the random variable x. Suppose we want the expectation of x squared. Well, we do a very similar thing. We just want the sum of x squared times p of x. So we just go to our probability distribution. We take each value of x, square it, times its probability of occurring. 1 squared times 0.048, 2 squared times 0.036. If we do that for all of our values, we end up with 1.92. So the expectation of x squared is 1.92. Now suppose we want to find our variance, or in other words, our expectation of x minus mu squared. Well, we go about it in a very, very similar way. Each x minus mu squared times the probability of occurring. So we would simply say, well, our first value is 0. We subtract the mean that we found previously, 1.2, square it, and multiply that by its probability of occurring. And we would do a similar thing over here. 1 minus 1.2 squared times its probability of occurring. We do that for all the values, add them up, and we get that this is equal to 0.48. So sigma squared, the variance of our discrete random variable x, is equal to 0.48. And if we wanted the standard deviation, sigma, the standard deviation of our random variable x, that is simply going to be equal to the square root of 0.48. Let's go back and take another look at this relationship. This relationship holds for any distribution, but let's verify that it works in our case. We just calculated that this quantity, the variance, is equal to 0.48. And we also calculated that the expectation of x squared is equal to 1.92, and that the expectation of x is equal to 1.2. And if we calculate 1.92 minus 1.2 squared, we'd see that that equals 0.48. So these two quantities are, in fact, equal. Now, we didn't have to actually use that relationship here because this quantity was quite easy to calculate, but sometimes this is a very handy relationship for us.